Now, let me introduce Anna Rechtman. So she's coming from Institut Fourier in France, and she's going to speak about existence of Birkhoff section for three-dimensional Reeb vector fields.
And this is it. Okay, well, thank you very much for the invitation to the organizers. I'm very happy to be here. I will talk about Birkhoff sections. So these are, many of the results are in collaboration with some set of these people. So Vincent Collin, Pierre Dornoy, and Umberto Hrinevich. You see that I wrote Pierre Dornoy in italics. That's for me not to forget to tell you that all the nice pictures were made by Pierre and not by me. Some people here heard me talk about similar things on Friday. There will be some overlapping, not too much, but a little bit. So the first two slides will be completely repeated from Friday's talk. So we'll be talking about flows on closed three manifolds. And I want to give you two examples before we start, and then start. And these are the same examples on Friday. So the first example is a suspension flow. So if you take a diffeomorphism of a surface, closed surface, and now you take your surface cross an interval, you can paste the two boundary components using your diffeomorphism. So this gives you a three manifold that fibers over S1. And now you put a flow on this manifold that is horizontal, okay? In the direction of the interval, and you're going to paste the entrance of the exit. So it means that this flow will have periodic orbits if the diffeomorphism had periodic orbits. This flow will have the same invariant sets as the diffeomorphism, etc. So in general, when you start with a 3D flow and you find such a structure, we're very happy because you reduce the problem in one dimension and you change continuous time for discrete time. So instead of studying this flow, you will study the diffeomorphism of the surface. I'm not saying it's easy, but it's time it doesn't get into your way. Okay, so obviously not all three-dimensional flows are like this. Life will be too easy. Especially because there are manifolds that don't fiber over the circle. Okay, so another example is the Hopf, what I call the Hopf flow. So let me start by telling you what the Hopf vibration is for those that don't know it. So consider the tree sphere. Okay, so you can think of it as the vectors with complex coordinates of norm 1. And I'm going to consider a function from S3 to S2. S2 think as a complex numbers where you add infinity, that is just sending the couple of coordinates into the quotient. Okay. If you think of the inverse image of, so I want to understand what's the inverse image of a point. You can think of 0, for example. If you think what's h minus 1 of 0, well, the first coordinate has to be 0, the second one can be whatever, but it has to be norm 1, so it's a circle. Okay, and in general, if you take any number, the inverse image will be this equation C1 equal to C times C2, and that's the plane. It's a complex plane that passes through the origin, intersects the sphere in a circle. Okay, so this fibration gives you the composition of S3 into circles. And now with a little bit of more work, you can show that any two circles will form a Hopf link. So they are as in a chain. I mean, if you have two pieces of a chain, okay? I don't have two hands to do it, so anyway. So now you can put a flow into this that preserves the circles. Okay, so this flow is moving all the points in the circles, and all the circles have period 1. You could choose another period, you could change the periods, whatever. Okay, and It's not a suspension flow, but I want to tell you that it's not too far of being a suspension flow. And the reason is that if you take any circle, it mounts a disk that is transverse to the rest of the orbits. Okay, so instead of having a closed surface that is transverse to my flow, I have now a disk, but the boundary is made of periodic orbits and intersects all the other orbits. So I can still look at the return map to this disk, okay, and study my flow from that disk instead of looking at the 3D picture. Okay, so this is an example of a Birkhoff section. It's the simplest example of a Birkhoff section. And now let me give you the definition of what a Birkhoff section is. So I will consider a closed three-manifold and go with a non-singular vector field. This always exists if you are thinking about it. So any three-manifold admits a non-singular vector field. And I will say that the vector field admits a Birkhoff section if you can find an immersed surface, a surface with boundary that is immersed in your manifold. I want the boundary to be mapped to periodic orbits, okay? The same as a disk before. And I want the interior of my surface to be embedded and transverse, if everything's oriented, you can say positively transverse to the vector field. And finally, you need to ask that every orbit intersects the surface in finite time, okay? And once you have this, it's like in the Hopf flow, you're happy you can look at the first return map on the interior that gives you a diffeomorphism of the interior of the surface that extends as a homeomorphism to the boundary. Okay, you will see that I put immersed and not embedded because you get more freedom. So what does that mean? It means that you can have two boundary components that are mapped to the same periodic orbit, or you can have a periodic orbit that a boundary component, sorry, that covers several times a periodic orbit. Okay, so I allow, let's say, weird things in respect not embedded things to happen at the boundary, but otherwise I want things to be embedded. I didn't say it, but there's not too many slides, so if you have questions, stop me, because if not, I won't go until the end of the time. Okay, so I want to tell you a little bit about Birkhoff sections, some of the results I know of Birkhoff sections on three manifolds. So the question you can ask is, if I give you a 3D flow, maybe all the flows have Birkhoff sections. Who knows? No? So does every non-singular vector field emits a Birkhoff section? So always in dimension 3. I won't write it again. Okay. The answer to this question is no, and there's at least two reasons for that. The first reason is that there are flows that are not suspensions without periodic orbits. Okay, so there's a big problem that is the quest of periodic orbits. If you give you a family of flows, do they have periodic orbits? Okay, they started with Poincaré studying the three-body problem, but we now know there are examples without periodic orbits in any closed three-manifold. Okay, give me any manifold, I will build you a flow without periodic orbits. So the first examples are of Paul Schweitzer, are C1 flows. Then Christina Cooperberg, so there's almost 20, I didn't put the dates, but Paul Schweitzer is in the 70s, Christina Cooper is 94. She managed to build infinity flows without periodic orbits that can even be made real analytic. And then you can add volume preserving. And if you add volume preserving, we just have, so far, examples are C1. We don't know to do better. Okay, so Greg Cooperberg, the son of Christina, was able to take Paul Schweitzer's example at doing volume preserving. Okay, so this is one first thing. If you have a suspension flow has no periodic orbits, no chance to get a Birkhoff section. Okay, second thing is non-transitive and also flows. Okay, if you have an Anosov flow that admits a Birkhoff section, the return map is a pseudo-Anosov map, and it's transitive. Okay, so if you have non-transitive Anosov flows, they don't admit Birkhoff sections, and Anosov flows that someone mentioned in the talks before, well, they are structurally stable. So it means that if you perturb them, you don't change the flow. So because you could change this question and say, well, maybe it's a generic situation. Every C1 generically, I have Birkhoff sections. The answer is no, because Anosov flows are structurally stable. Okay, so you cannot aim for this. Okay, but I could add volume preserving. So next question, what if I give you a volume preserving vector field, does it have a Birkhoff section? And the answer, or the guess, is there's no answer. The guess for this question is that it's yes. And this was conjectured by Etienne Gis and François Béguin. Because you have Anosov flows, so Anosov flows give you an open C1 set that you cannot put a Birkhoff section there. It's because I put volume preserving. Okay, so now my flows, Anosov flows are transitive, and I can do it. There was another question? No. Okay. And so I will announce one theorem by us, and I will come back to it later. So, well, one good news for this conjecture is that you can create periodic orbits by C1 perturbations. This is a closing lemma of Charles Pugh. So periodic orbits won't be a problem. And the volume preserving hypothesis takes the Anosov problem from the way. Maybe there are other problems, I don't know. I don't know that many obstructions to having a Birkhoff section other than the ones I put. Okay, so one of the theorems I want to explain you a little bit, further in the talk, is that among a family that's called Reeb vector fields that I will define in a few slides, there are volume preserving vector fields. Having a vector section is not just C1 generic, it's infinity generic. Maybe it's true for any Reeb vector field. Who knows for the moment. Okay, so now I want to tell you about a few families of flows that I like and what I know about periodic orbits and Birkhoff sections. Okay? I don't know if this is an exhaustive set of statements. What I know is it's an exhaustive set of statements of what I know. Okay, so Anosov flows. So now everything is three manifolds, volume preserving, non-singular. Anosov flows have many periodic orbits. Everyone here knows that. They're even dense. And David Fried in the late 70s proved that they always have Birkhoff sections. Okay? Once you have a statement like this, what I would love to have is, and many people, is a statement about the complexity of the Birkhoff section. And especially about the genus of the Birkhoff section. Boundary components, we care less than the genus. There are new constructions of Birkhoff sections for Anosov and pseudo-Anosov flows on three manifolds by Chik-Chuk Tsang, where he can control the number of boundary components. So there are Birkhoff sections with two boundary components, but the bound on the genus, he has a bound of the genus, but it's huge. So not very useful. And it's a completely different technique than what Fried did. I won't talk a lot much of techniques, but I will make comments about it. And please ask me questions if you have. Okay, next set of flows, geodesic flows. So you take a surface, I will make an example in a minute. You take a surface with a Riemannian metric and you consider the geodesic flow on the unitary tangent bundle of your surface. So these have infinitely many periodic orbits. It's a long story. I put 3 dots. I don't even know it completely, but there's a long story of finding closed geodesics on surfaces. And so now we know this. And it was proved a year ago that geodesic flows always have Birkhoff sections. There's no genericity, it's always. Every geodesic flow of a C2 metric, I will say, has, or maybe C3, but some differentiability, has a Birkhoff section. This was proved by Marcelo Alves and Marco Mazzucchelli. The construction of Birkhoff sections for geodesic flow started with Birkhoff, and that's why we call them Birkhoff sections. So again, I will repeat from Friday, but I will give you an example of a Birkhoff section for a geodesic flow. So as I tell, so what a geodesic flow is, you give yourself a closed surface with a Riemannian metric. Okay, so now if you take a point on your surface and you pick a vector tangent to the surface at that point, they define together a unique geodesic. Okay, now I'm going to take my vectors to have norm 1. Okay, so you have a unique geodesic, and the flow we would do is move the point along the geodesic distance t and push the vector so that you continue to be tangent to the by parallel transport, but just the tangent vector to the geodesic at the point where you stop. And this defines a flow on the unitary tangent bundle of your surface that is a closed trimanifold. Okay, and Birkhoff considers some cases, and one case that he considered was a case of S2 with a metric of positive curvature. If you prefer the round sphere on, the unit sphere on R3, that's fine. Okay. So what he proved, and it's a very nice proof if you don't know it, is that you can find a simple closed geodesic, so a geodesic that has no intersection points, that we'll call the equator in the following, that has the following amazing property. If you take any other geodesic, so this geodesic will split your sphere in 2 parts, in 2 disks, okay? We call the north hemisphere and the south hemisphere. And every other geodesic cannot stay in one of the 2 disks. So it has to, if it starts in north, it has to go at some point to the south, and then at some point to north, and et cetera, et cetera, et cetera, okay? So now I want to build a Birkhoff section out of this closed geodesic for the flow on the unitary tangent bundle, okay? When you have a closed geodesic in the surface, it lifts to 2 periodic orbits because you can orient it in 2 directions, okay? So you have 2 lifts to your periodic orbit, okay? And now what Birkhoff did is you choose one of the 2 disks. So here I choose the north hemisphere, and for every point of this equator, you're going to take all the unit vectors that are either tangent to the curve or point towards the north hemisphere. Okay, and you do this at every single point of the equator. When you lift this to the unitary tangent bundle, what you get is an annulus, because it's a circle cross an interval of vectors. So it says 1 cross I. The boundary of the annulus are the 2 periodic orbits, the 2 lift of the equator. So this is embedded surface with boundary. And this thing that all the geodesics have to go from north to south to north back means that at some point they cross from south to north. And at that point they cross the annulus at the top. So this is a Birkhoff section for the geodesic flow of any positive curvature sphere. Questions? Okay. So he did many more things. He treated the case of hyperbolic surfaces, but I won't do that today. And I will go back to my table. Look at the time. Okay, so we were here. So I can say something about the proof of Alves and Mazzucchelli. So they do it with the construction I just did. Just need to find enough periodic orbits to cross all the geodesics somehow. Okay, so the next family, that's the one of the theorem that I mentioned before, are Reeb vector fields. So you will see that there are two lines between a nosoph and geodesic, and just one line between geodesic and Reeb. It's not a mistake, it's because every geodesic flow is Reeb. Okay? And nosoph flows, there are flows that are a nosoph and Reeb at the same time. Okay? But there are also nosoph flows that are not Reeb, even in the conservative case. Okay. So for Reeb vector fields, it's in blue because I will define it in a while. We know that there is at least two periodic orbits. So the existence of the first periodic orbit was proved by Tobbs. And then this was upgraded to two periodic orbits by Christopher Gardiner and Michael Hutchings. So Tobbs is 2007, and the second theorem is 2016, if I don't mistake it. And as I told you, so we now know that infinity generality, we always have Birkhoff sections. I won't discuss more about this. You can generalize a Reeb vector field to what is called a geodesical volume-preserving vector field. Geodesical, what it means is that you can find, so you have a flow, you can find a metric that makes all the orbits geodesics. Again, Reeb vector fields are geodesical, but suspension flows are also geodesical. Okay? In this case, there's always a periodic orbit if M doesn't fibers over S1, and we completely understand the cases without periodic orbits, and even with a finite number of periodic orbits. You can list them, there's not too many. And in this case, with Robert Cardona, we were able to prove that C1 generically, you have always Birkhoff sections. There's another family of flows that I like a lot, for which I don't know anything. And these are solutions to the Euler equations of hydrodynamics. So the simplest Euler equations. So they don't depend on volume, on time, they have no friction. I mean, the simplest Euler's equations. And I don't know if they have periodic orbits, and obviously I don't know if they have Birkhoff sections. The reason why they are here, well, one is because I have thought a lot about them, but the other is because these examples without periodic orbits cannot be made in this category. Okay. Okay, so now Reeb vector fields. So a Reeb vector field is associated to a contact form. So to define a contact form, let me start by defining what a contact structure is. A contact structure is a plane field that is nowhere integrable. So what this nowhere integrable means is that you cannot find even locally a surface. So a plane field, as I mentioned too, so if you had a surface that you can look at the tangent space of the surface, that gives you a plane field. But the non-integrability means that you cannot find even locally a surface that is tangent to this plane field. A contact form defining the plane field psi, it's a differential one form whose kernel is psi. Okay? And this non-integrability condition transforms into this equation alpha product with the alpha cannot be zero. Okay? So that means that the kernel of alpha is a two-dimensional thing, is my plane field. The kernel of the alpha is a one-dimensional thing. This thing that they are not zero means that they're always transverse. Okay, so to this form alpha, we associate a Reeb vector field, or vector field that is called Reeb, that is in the kernel of the alpha, so in this one-dimensional direction that my one form gives me. And then I choose the size of the vector field by saying that alpha evaluated on x has to be equal to 1. Okay? So as I told you, geodesic flows are Reeb, and also they appear in celestial mechanics and in general in Hamiltonian dynamics. Not all the levels, I mean, not all the vector fields are Reeb, but there are many Reeb vector fields. Yeah. So it is now known that every three-manifold admits a contact structure. It's even better. You have a contact structure in every homotopy class of plane fields. Okay, so there's a lot of contact structures. It's not a funny thing. There's a Darboux theorem. So locally, every contact, I should put structure, not form. Every contact structure looks like the kernel of dc x dy. Okay, so locally they all look the same. It's globally that they're very different. As I said, geodesic flows are Reeb, and suspensions flows are not Reeb. They cannot be Reeb because if you have a closed surface transverse to a Reeb vector field, the differential of the contact form, so d alpha, restricts to an area form on the surface that is exact, and that cannot happen by Stokes' theorem. And the other thing I want to tell you is, so I said you have a contact structure, you can choose a contact form, and the contact form gives a Reeb vector field. I choose the contact form. So to a given contact structure, I can associate many Reeb vector fields. Okay? Because if I take a contact form alpha and now I multiply by a non-zero function, the structure doesn't change, the kernel is exactly the same, but the differential changes, and it doesn't change just by the size, it changes really of direction. Okay, so you can have, for the same contact structure, you can have flows are, all the orbits are periodic, you can have flows that have just two periodic orbits. There's, I mean, the contact structure can tell you things about the Reeb dynamics, but not too much. You have a lot of freedom. Okay, so now let me go back to my theorem. Okay, so give yourself a contact manifold. So I fix the contact structure. And the theorem says, so it was proven independently by us and Gonzalo Contreras and Marco Mazzucchelli, then among the Reeb vector fields of this contact structure, having a Birkhoff section is infinity generic. Okay, so I won't say much. I will say a few words about the proof in a minute. I just want to say that this infinity generic is not a perturbative thing. It's a set of hypotheses that we know they are generic. So the first hypothesis is non-degeneracy is in both. And I will explain you why it's in both in a minute. Non-degeneracy means the following. When you look, so I will say what it means for a periodic orbit to be non-degenerate. And a flow is non-degenerate if all the periodic orbits are like that. So when you look at a periodic orbit, you can fix a small transversal to your periodic orbit and look at the return map in the transversal. Okay, this is a diffeomorphism. Define it like in a very small neighborhood of the point where your transversal intersects the orbit. And if you take the differential of this thing, okay, it's a 2x2 matrix. My flow preserves volume. Forgot to tell you why, but I can tell you in a minute if you. And so this matrix has determining one and has either real or complex eigenvalues. So if it's real, I will ask that one is not an eigenvalue. So I have a hyperbolic periodic orbit with a direction expanding and a direction contracting. And if they are complex, I will ask that my matrix is irrational rotation. Okay, so this means that I never have one as an eigenvalue if I want to go several times along a periodic orbit. So I didn't say it because I forgot, but the reason why these vector fields preserve volume is because they preserve the contact form that defines them, alpha. And so they preserve alpha wedge the alpha. That is either a volume or minus a volume, but it's like a volume. Okay, so that's the first generic hypothesis, that's the self-infinity generic hypothesis. So we proved the existence of a Birkhoff section using non-degenerate and equidistribution of periodic orbits. So equidistribution with respect to this invariant volume. So it means that you can find bigger and bigger collections of periodic orbits such that there is a measure supported in these periodic orbits that tends to the volume. Okay, and this is not normally a generic condition, but it is among Reeb vector fields by a result of Fourier of 2021. And Mark Mazzucchelli and Gonzalo Contreras, they prove it for non-degenerate Reeb vector fields if you assume also that the intersections of stable and unstable manifolds of periodic orbits are transverse. And again, this is generic among Reeb vector fields. Okay, so now we'll say things that are going to be a little bit not understandable, or would last for a few minutes just. So what are the ingredients of both proofs? The main ingredient to the two proofs is the existence of something that is called broken book decompositions. I won't explain. If someone has a big desire afterwards to know, they can ask me. I will. It took me like 40 minutes to explain it on Friday, so skip it that way. So it's a system of transverse sections, okay, but not just one, many. So it's a system of surfaces with boundary that decompose the dynamics. And from this, we unbroke the broken books by creating Birkhoff sections. Okay, the broken book decomposition, so I hadn't not the time to say it on Friday, and I will say it now, they use strongly embedded contact homology, and that's a theory that was developed in the last 20 or 25 years by Michael Hutchings that gives you a lot of information about Reeb vector field and combines it with techniques of Reeb. The techniques of Reeb reappear when you want to go from a broken book decomposition to a Birkhoff section. Okay. So now I want to tell you a little bit of, I want to tell you two applications of the existence of Birkhoff sections. Okay, and one is a result on Legendrian knots. Okay, so when you have a contact manifold, you have this plane field. And if you look at orbits of a Reeb vector field, they are always transverse. But now you can look at knots that are tangent, always tangent to the contact structure. These are called Legendrian knots. Okay, and Arnold conjecture that if you have a Legendrian knot in a contact 3 manifold, you can always find a piece of orbit of a Reeb vector field that starts at the Legendrian and ends at the Legendrian at some other point. Okay, so you have a knot that is tangent, and now you look for a piece of orbit of a transverse vector field that starts and ends at the Legendrian. Okay, the proof of this conjecture is, again, Michael Hutchings and Dobbs in 2011. They gave the existence of one Reeb chord. And we will be able to prove, and it's actually quite simple, is that if you have a Reeb vector field that admits a Birkhoff section, then you have many, infinitely many Reeb chords, unless you are in the case where the vector field has exactly 2 periodic orbits, and the Legendrian intersects both of them, and many other things, okay? So let me comment a little bit on this. So when you have a Reeb vector field on a 3 manifold, I told you there's always at least 2 periodic orbits, okay? It is conjectured that it's actually 2 or infinitely many. This is known if you have a Birkhoff section, okay? If you have a Birkhoff section, you have 2 or infinitely many. So my hypothesis of the theorem imply already that my vector field will have exactly 2 or infinitely many. The case of two periodic orbits is very well understood. The manifold has to be either S3 or a length space. The two periodic orbits form a Hopf link, as in the Hopf vibration. You have a transverse annulus. We understand everything. Okay. So this is some analog to that. And it proves a result of Serre, which I was very happy to discover. I was not aware of this. So if you take a Riemannian surface and you take a point, the fiber in the unitary tangent bundle is tangent to the contact structure. Okay, so it's a Legendrian knot. Okay, and now you can ask, as Vivenka told us on Friday, I think you can count the loops that start at that point and end at that point in the surface. Okay, these are pieces of the Reeb orbits of the geodesic orbits of the geodesic flow that start at end at the Legendrian. Okay, and it's known since a long time ago that there are infinitely many. Okay, and well, our theorem implies that also. It's a different proof, not simpler, just a different proof. Okay, so that's the first application. I don't know how I'm doing on time. What? Okay, so I think I will end a little bit before, but that's fine. The other, okay, maybe I can say a word of how you prove this. I will leave this so I can use my hand. So assume, so you have a flow here, living here. You have a Birkhoff section. The Birkhoff section is here. You have a Legendrian knot, and let's assume, just to simplify it, and I'm not saying I will cover all the cases, but I will tell you the idea of the proof, that your Legendrian knot doesn't intersect the section. So the Legendrian knot is somewhere over here, and you have the section. Okay, I have a flow, so I can project back my Legendrian to the section, okay, by flowing it backwards. Okay, it gives me a closed curve in my section. Okay, and now, well, maybe it already has intersection points. So if when I project, I get something that is not embedded, that intersection, self-intersection point of the curve corresponds to a Reeb chord, because it means I had 2 points in the same orbit that got projected to the same point. Okay, so what I want to do is to find a lot of intersection points. Okay, and now what you're going to do is take this curve that maybe it's simple at the beginning, who knows, okay, and you push it and you take the image by the first return map. Okay, okay, my curve, well, it turns out I have not only a surface, but I have an area form, and I have an exact area form that has to be preserved by the return map. Okay, so now I use that with Stokes to eventually find intersection points, because I cannot have like infinite volume. And once you find one, you find another one, and etc. So it's an application of Stokes' theorem, this theorem. Okay, next application that was much more complicated is if you think of topological entropy of the flow. So I put this, but now maybe it's everyone knows. So if a flow on a three manifold has positive topological entropy, it means that there is a horseshoe somewhere. Okay, so if you want to prove that a flow has positive topological entropy, you have to look for a horseshoe, and a horseshoe is, as someone drew it on the blackboard, is a hyperbolic point with a homoclinic intersection. It's not the right picture, it's more or less a good picture. Okay, so using Birkhoff sections, we were able to prove that the set of contact forms of a given contact structure whose flow has positive topological entropy is, I mean, especially dense with respect to this infinite topology. this uses Patrice Le Calvez techniques. And even more, we can prove that under some other generic hypotheses that include equidistribution, transverse of intersections, and undegeneracy, actually every hyperbolic periodic orbit has homoclinic orbits in like everywhere. And this uses as result of Patrice Calvez and Martin Sambarino. Well, this is a proof of the result that is for diffeomorphism of closed surfaces. So in general, when you have a flow with a Birkhoff section, I told you have a diffeomorphism, and somehow it's not easier, but a different problem. You want to adapt things, you have to be careful about the boundary. So what is used in here is, and they prove that generically for a diffeomorphism, every hyperbolic periodic orbit has a homoclinic intersection. What is used here is exactly the same proof, but you have to take care of the orbits in the boundary, because when you collapse, so if you want to go from a Birkhoff section with a return map to a closed surface, what you want to do is collapse the periodic orbits in the boundary. But when you collapse the periodic orbits in the boundary, you don't necessarily get something that is non-degenerate. Okay, you can get things that are like have many stable and unstable directions, and you have to take care of these cases somehow. Okay, so I will stop here and thank you very much.